Okay, so I start by thanking the organizers for giving me the opportunity to present my work here. So I'll be talking how can I get sub-theorems from intrinsically Carrollian way. So of course the motivation is flat holography. Let's state the principle once more. The holographic conjecture states that a quantum theory of gravity should have a dual description in terms of a field theory without gravity, and that resides on a lower dimensional boundary. So the most well-known example is ADS CFT, but certainly uh, the flat space, asymptotically flat space is closer to reality than asymptotically ADS. So that's why you're interested in flat space holography. So the most well-developed formalism till date for flat space holography is celestial holography, where the celestial conformal field theory resides on the codimension 2 celestial sphere at null infinity pi of the asymptotically flat space-time. So the celestial conformal fields depends on two coordinates. So those are celestial sphere stereographic coordinates, and further they are labeled by a continuous boost weight. So I shall denote it by delta with subscript C. Now, a single massless bulk field corresponds to an infinite family of celestial conformal primaries. So that's how the dual theory is effectively three-dimensional. So two coordinates z bar and another parameter that is this continuous boostoid. So the motivation behind this celestial holography was like this. So the asymptotic symmetry algebra at the null infinity of the 4D AFS is the extended BMS4 algebra. Now, the starting point of the celestial holography is the observation that the bulk subgraviton theorems can be interpreted as the word identities of the extended BMS4 symmetries. Furthermore, the currents that generate these word identities were built explicitly from the components from the asymptotically flat spacetime. So in most of the works in celestial holography have been like this. So starting from the bulk theory, or at least they need some hint from bulk theory, and then try to map those things in familiar forms from 2D conformal field theory. So, but purely boundary theoretic construction that is completely independent of hints from gravitational physics is missing for most of the aspects of celestial CFT. So here I will try to show that you can abstractly define Carrollian conformal field theory and try to find some aspects of the bulk gravitational physics just from symmetry principles. So the Carrollian holography. So in the Carrollian holography is codimension 1, and it is closer to our well-known ADS CFT. Here the in addition to the two stereographic coordinates, the Carrollian conformal fields also depend on null coordinate, one of the null coordinates. So in some sense, the celestial continuous boostoid has been traded for the null coordinate. And further, the starting point of the Carrollian holography is this observation by Gibbons, Duhamel, Horvath, that the extended BMS4 algebra is isomorphic to the local conformal extension of Levi-Leblanc's Carrollian algebra in 3D. The global subgroup is ISL2C, that is of course isomorphic to the bulk Poincare group. So that is why we think that the field theory, the codimension 1 field theory on the null boundary should be Carrollian conformal invariant. Now, in line with the ADS CFT extrapolate dictionary, we expect that a single Carrollian conformal field theory will correspond to one bulk massless field. And if you remember, for the celestial case, it was the 1 versus infinite family correspondence. Here we expect 1-to-1 correspondence in line with the ADS CFT extrapolate dictionary. Okay, so let us briefly look at the transformation rules for this Carrollian Carrollian conformal transformation rules. So equation 1 describes the transformation that are globally defined on the sphere, and actually R cross S2. So these are the global defined transformation. But in 3D, there is infinite extension to this globally defined transformation, and these are holomorphic these are holomorphic 2D CFT-like extension. These are given by this. So Z can be transformed into any holomorphic function fz. Similarly, Z bar can be transformed into any anti-holomorphic function, and T under these two transformation changes like this, and this is the super translation part. Okay, so the vector fields that generate these transformations on the space of functions are given by 3, and of course they satisfy the extended BMS4 algebra. So this is just the algebra of differential operators that generate the extended Carrollian conformal transformation. So of course we have 10 generators for the global Carrollian conformal transformations, and this is exactly matching with the number of generators of the ISO 31 Poincare. Okay, so and these are the primary transformation rules. These may look familiar to 2D CFT like transformation rules, except that there is one extra time coordinate also. Okay. Let's now directly proceed to the word identity. So I'll be deriving these stress tensor word identities directly from symmetry principle in exactly the same way we do for 2D CFTs. So following the same method, so we find that the stress tensor word identities of a Carrollian CFT on a 3D Carrollian flat background with topology R cross S2, and we further assume that there is Weil invariance in the theory. So with this kind of symmetries, the stress tensor word identities are found to be these 4, 6, 7, 8, and 9. So other than these 4 word identities, so we find no new word identities correspond to other local symmetries. Okay? So the word identities, so delta P is the Carrollian scaling dimension, SP is the Carrollian SO2 spin, type is the representation of Carrollian boost matrix. So when psi is a matrix representation, it is usually reducible but indecomposable representation. Okay, translation is usual. So now I shall show how to take linear combination of these word identities and find the leading and the sub-leading subtheorem. Okay, so we take this certain linear combination here and find equation 10. Now it looks like the left hand side is a one-dimensional PD, partial differential equation with delta t, and the right hand side can be, or right hand side is a simple function, so we can just as well solve this PD to get an answer for this TTT correlator. But of course we need an initial condition, so I choose the advanced initial condition that is natural from gravity perspectives, like spacing. It's natural from the point of view of specifying these asymptotic initial conditions on psi plus minus. So the advanced initial condition, and the solution turned out to be equation 12. So there the important feature is that there is one temporal step function. Okay, so now we see that this word identity is containing contact term singularities on the S square. So I would like to make those contact term singularities into pole singularities, and we'll show that while doing so, we'll recover the Weinberg soft factor. Okay, so we can just extract these two Delver operators from the right hand side, and so this is the identity on the right hand side. And now we shall now invert this Delver 2 operator to define a new field. So invert this Delver 2 operator and we define this new Carrollian field S0 plus, and this is the definition of our new field. So of course the field S0 plus a scaling dimension delta equal to 1 and spin 2. The counting can simply follow from here. Okay. Now the S0 plus word identity with a string of Carrollian conformal primary multiplets is given by equation 15. So these word identities are exact only up to some temporal contact term. So I am considering non-coincident temporal insertions so that the temporal contact terms are not giving any contribution in position space, but we have to be careful because if we blindly Fourier transform this, there can be some non-zero contributions coming from these temporal contact terms. So in position space, this is fine, equation 15. So, and 16, these two constraints simply follow from 15. So we'll see. So since we recognize this as the Weinberg soft factor, if we just turn off this psi p and psi p bar, this is recognized with the Weinberg soft factor. So this temporal step function here captures the essence of the 4D bulk AFS super translation memory effect. So this is really showing a shift between the early time value and late time value of this left hand side correlator. Okay, so to more directly see this soft factorization, so we can just temporal Fourier transform equation 15. So we can be motivated about doing the temporal Fourier transform this way. One is Strominger triangle. So there is this relation between soft theorem and word identity. They are related by simple Fourier transform. Or the another way will be to be thinking about the Carrollian holography, Carrollian holographic prescription, like the bulk null momentum space scattering amplitude is just the Fourier transform of Carrollian conformal correlators. So there are two motivations to consider the temporal Fourier transform. So we have to Fourier transform only to the t to omega space, so only temporal Fourier transform, and then we have to explicitly take the omega tends to soft limit only for this S0 plus field. So if we do that, we will exactly recover the Weinberg leading soft graviton theorem when this is 0. Okay. So since we require omega tends to 0 explicitly in the T space, this translates into the fact that the word identity 15, so this is describing the positive helicity leading soft theorem only at the particular value t tends to minus infinity. So what does it describe for other values of t? Well, we will wait and see. But right now, because of the other temporal contact term contributions, I can only certainly comment about its value at t tends to minus infinity, where those contact terms will not contribute. Okay, and this is a comment like the word identity is the Carrollian CFT counterpart of the 2D celestial leading conformally soft graviton theorem. Now, of course, we can decompose this S0 plus field inside the correlator like this. So since this is a linear polynomial in Z bar, we can use this decomposition and see that this new kind of semi-modes P minus 1 and P0, they are exactly holomorphic in the non-coincident limit. So these looks, this P minus 1 and P0 looks like some holomorphic currents from 2D CFT, but we will not be so hasty about these interpretations. So we can similarly build a negative helicity field and that satisfy this relation. Okay. well, S naught plus satisfy this relation and S naught minus satisfy this relation. So that means they are really related. And we can just observe that S naught plus and S naught minus are related by 2D shadow transformation. Now, one special feature about this TT is that this TT is a primary descendant or null field, because so we'll later see that S naught plus is a Carrollian primary field and TT is also is a Carrollian primary field. Okay, and as we have seen by construction, TT is a Lorentz descendant. Now both are Carrollian primaries, and moreover the TT word identity equation 12. Okay, so this one, so this is vanishing in the OP limit when no operators are coincident. So this motivated me to comment, to make this comment like TT is a null field, and it seems consistent with the conclusions of this paper. Okay, now we can do the same exercise with the super rotation word identities. So we just really use the translation and boost word identities to get these leading soft theorems, and we can use the other soft theorems like rotation and scaling and make this linear combination. It doesn't look nice anyway. So the important thing is equation 19. So left hand side there is this del t and there is this del z. So we'll be inverting this del t operator here first. Okay, and see, we'll get a theta function from here, and we'll get a t theta t kind of dependence from here. And under again I am choosing an initial advanced initial condition like this. So solving this temporal uh, partial differential equation, the solution is obtained as equation 21. Okay, so now again I would like to make this these sphere contact terms into some powerless singularities while having branch cuts. So it turns out that a good way to do is to extract a del bar cube derivative from right hand side and invert that to define an operator like equation 22. Okay, so and dimension of this S1 plus field is 0, 2. In is 2, delta is 0, and the S1 plus word identity with the Carrollian conformal primaries is given by equation 23. And 24 simply follows just from the, okay, you can simply observe this, that equation 24 is true. Now again, if we do Fourier transform of this word identity 23 and explicitly impose the soft limit only for S1 plus, we obtain a Laurent expansion. So the coefficient of the leading 1 by omega square pole is the Weinberg soft factor, and the coefficient of the leading 1 by omega pole is the Kazhajos-Strominger subleading soft factor only when the prime, all these primaries have this, and importantly they have this delta equal to 1 scaling dimension. Okay, and further we have to identify the Carrollian spins with the helicities of the 4D massless particles. Okay, so since we have reached the super rotation, subleading soft theorem from this equation, so it seems that this theta function is really telling us about the super rotation memory effect in equation 23. So this theta function is telling us about super rotation memory effect. Now this delta equal to 1 condition is of course have been derived in the literature in several ways. So one of the ways is to analyze the radiative fall-off condition of the bulk massless fields. This was done in the first this reference, and the second most recent one is a purely group theoretic approach that was taken in this reference. Well, so well, I don't exactly remember. So check it. So So it was for general D, as you remember. So we'll have to check. And so now, of course, so guided by this 16 and 24, 24 is this. So let's look at this equation. So this equation is telling us that we can make an decomposition of the S1 field inside the correlator like this, where this S1E part is time independent in the OP limit because of this relation. And okay, so this del bar cube S1 plus is 0 in the OP limit also, and it follows from construction. So this S1E part of this S1 word identity is actually describing the subleading energetically soft theorem part explicitly when t tends to minus infinity. So we are kind of projecting out only the subleading soft theorem, and clearly this then this word identity, S1E word identity, is not a word identity in the truest sense, because S1E is not a Carrollian field at all. It is some collection of new modes. So this S1X word identity is just the 3D Carrollian conformal counterpart of the 2D celestial subleading conformally soft graviton theorem. Here we have these Carrollian weights. Oh, and we have to distinguish them with the celestial, between them and the celestial weights. So, now, okay, by doing the same exercise, you can also build a new field T, and from this T field, you can actually get a hint of the 2D celestial conformal stress tensor word identity. So the derivation is similar, so you have to just extract one del bar operator from both hand sides and invert it. So I'll just directly quoting the result, so we can get a hint of the celestial stress tensor identity. Now I would like to talk about Carrollian conformal OPs. So okay, so why is that important? So till now I have only talked about leading and subleading soft graviton theorems, but you know, so in Einstein gravity there are subleading soft graviton theorems, but that are not universal in the sense that they can be uh, modified by Wilsonian corrections, but at least for some, okay, so, but at least for some theories like Einstein gravity, we can have the subleading soft graviton theorem. So we'd really like to capture the signature of the subleading soft theorem also, but there is no direct construction in terms of the Carrollian stress tensor identity. So we'll have to take a different route. So for this, we will now need to look at the Carrollian conformal OPs. And for discussing on OPs, I find it convenient to introduce a J epsilon prescription. So J epsilon prescription, so it's similar to I epsilon prescription, I will say, but since I is already taken inside Z, so I am writing it as J. So it's a kind of second complex unit. So just you have to, for now, just trust me that this S naught plus correlator can be written like this in the J epsilon form, where the denominator, this quantity in the denominator is actually this. So epsilon is infinitesimal 0 from the positive side. Okay, so the important point for us will be that this 1 by delta z tilde quantity reduces to 1 by z minus zp only when tp minus t is greater than 0, and it is 0 when tp minus t is less than 0. So this is really valid in a sense of distributions. So, and this is capturing the defining property of the temporal step function. Thus, when t tends to minus infinity, see, when t tends to minus infinity, this quantity is positive, and for t tends to minus infinity, this quantity is always same as 1 by z minus zp. Okay, now equip with this j epsilon prescription, we shall now proceed to discuss on OPs. So the OP is corresponding to the S naught plus word identities that we discussed before. So this can be written like this. So how can we see that there are these extra terms like higher order poles? Okay, you can just follow the BPZ paper and follow their construction, and you'll see that they happen. And similarly, in the so the first line is modulo terms holomorphic in this quantity. So there are regular terms, and since this phi is not a primary field, so it's a generic field, non-primary generic Carrollian field, so it can have higher order poles also. So you can see, just take descendants of the primary so primary OP, just take descendant and you will recover these higher order poles. The important thing is that there are also regular terms. Okay. Now this relation 32 and 33, so they are exact in the OP limit, since all the other contact terms will be vanishing in the OP limit. And for Carrollian conformal primary, we specially have these conditions. So that we have already seen from our word identity derivation. So no higher order poles than the one we have seen before for Carrollian conformal primaries. Now similarly, you can write the S1 plus OP. So due to lack of space, I am writing the left hand side like this. So you can write this, and you see then again equation 35 and 36 are exact in the OP limit, and for Carrollian conformal primary multiplets, these are satisfied. Okay, so now this how to get this W1 plus infinity symmetry just from symmetry principles. So as I said, I would like to really encode the sub-subleading sub-graviton theorem, and taking cues from what we have seen before, like this relation del T S1 plus minus S naught plus is 0 in the OP limit, and we have seen that S1 plus word identity contains leading and sub-leading sub-graviton theorem. So I just took the cue and proposed that we need to have a field in our Carrollian conformal CFT that satisfy this equation 37 exactly in the OP limit. Okay, so I am introducing some non-universal feature in our Carrollian CFT. So the universal fields in the Carrollian CFT are these three fields: S naught plus, S1 plus, and T. They are built out of Carrollian stress-tensor, and stress-tensor is present in any translation invariant theory. So now I am introducing some non-universal feature by assuming the existence of this S2 plus field that satisfies this relation in the OP limit. So of course, you can see that the S2 plus field has dimensions delta S to be -1, delta -1, and spin to be 2. Okay, so due to this relation, the decomposition follows. S2 plus can be decomposed inside the correlator like this, and this S2E quantity is time independent in the OP limit, and this S2E part has to contain some new modes that has not previously been appeared in the S1 plus or the S0 plus field. Now we shall see that when we are trying to construct the S2 plus OP, we will need an infinite tower of local Carrollian conformal fields like S plus 3, S plus 4, so all these kind of infinite tower. So they must automatically exist in our Carrollian conformal field theory if this S2 plus OP is needed to be consistent. Okay, so let us start. So it's a long way, so I can take time, right? So it's already half an hour. I've got no questions till now. So, huh? So Yeah, so how to construct these OPs directly from symmetry principles. So what is interesting for our purpose is to find the singular terms of the mutual OPs of S2 plus S2 plus, and for that we'll need the knowledge of the mutual OP between S0 plus and S1 plus, and I shall fix them by demanding that the OP commutativity property holds. So I shall assume that the bosonic commutativity property holds, and then I shall make ansatz about the generic. Uh, so I know how the generic S0 plus S1 plus OP look like, right? So a generic S0 plus OP will look like this, and the generic S1 plus OP will look like this. So we can just follow this ansatz, but we also need to truncate the higher order poles at some order to get some conclusion. So this is also done in 2D CFT literature. So you can find the stress tensor TTOP from this kind of symmetry arguments using just OP commutativity property. But there you need to also impose the unitarity condition that all the fields are uh, h greater than 0, like holomorphic weight is greater than 0. So if you impose that assumption by hand, then you can find the TT correlator mm, just using the symmetry principle. So I am just doing that same exercise for our Carrollian conformal theory. But here we see that we already have a negative scaling dimension field, but I cannot just impose that delta negative cannot happen. So instead, I impose that no time independent local field in the theory poses negative Carrollian scaling dimension. So you see, so S2 was a time dependent field. So I circumvented that example by imposing that no time independent local field should have negative scaling dimension. Moreover, the time independent local field with delta equal to 0 and S equal to 0 is uniquely the identity operator. So this is the assumption, and this second assumption that the fields S0 plus and S1 plus are Lorentz quasi-primaries uh, are borrowed from celestial CFT literature. So under these assumptions and respecting the answers that I showed you, so we can directly find the S0 plus and S1 plus OPs like this, completely fixed. And now from the knowledge with of this OP is 39, we can fix this S0 plus S2 plus OP to be exactly this. So we are also using the two assumptions that I mentioned. Now once we know 40, we can find the singular term of the S2 plus S0 plus OP directly by using the OP commutativity properties and the restrictions on the S1 field. So restrictions like 32, 3. So 32, 3 is this. These are the restrictions, like you have to be truncating in the linear order. So and S0 plus is time independent OP limit, 35, 6 is this. So we have to be using these constraints, and then you can find the S2 plus S0 plus OP directly from the bosonic commutativity relation. So similarly, you can also find the S1 plus S2 plus OP. And now one thing is that, so S1 plus S2 plus OP is directly fixed by our ansatz and the assumptions. Okay. Now to fix the S2 plus S1 plus OP, we need to know whether this S2 plus operator also have, if this S2 plus operator also have this similar kind of truncation property. So we have to figure that out first, and we have found that indeed it truncates at the cubic order. So equation 42 is an exact relation for S2 plus in the OP limit, and I have inferred this by looking at the S0 plus S2 plus OP and acting with this operator, and since this is 0 by bosonic commutativity property, And then I demanded that the Carrollian conformal OPs must be associative just as they assume in 2D Euclidean CFT. Now this assumption may be a little tricky because we know that in celestial CFT the associativity is not that well established, but anyway I assume this to be true. Okay, so thus this 42 says that this S2 plus phi OP must be a cubic polynomial. Fine. So now, since after we have found the truncation, we can directly find this S2 plus S1 plus OP from bosonic commutativity. And now we are ready to find this S2 plus S2 plus OP. Okay. So for S2 plus S2 plus OP, we have to make an ansatz that is respecting all the constraints on S2 plus. So like these, and there is one constraint like this. So respecting all these constraints, I make an ansatz for the S2 plus OP. So this is truncating in the order 3 for anti-holomorphic variables. So this is our ansatz, and now we can find this S2 plus OP from the knowledge of this S2 plus S1 plus OP in this way. Like if you take del TP, derivative of 44, then it must agree with this S2 plus S1 plus OP because of our defining relation 37. Is this because of this relation, these two answers must agree. So, and this imposes some constraints on the fields, the undetermined fields. So these are listed in 45, and we see that all the local fields with s greater than equal to 2 here and a01 are time independent, and moreover they have delta less than 0. So they are set 0 by first assumption. Now the more interesting constraint is coming from the second line. Look, I have found a local field. So there must exist a local field in the OP expansion A11 whose time derivative is proportional or not proportional, is exactly equal to 6s2 plus in the OP limit. That means I have to have a field S3 plus that satisfies equation 46 in the OP limit. 46, this follows exactly again the same thing that I have done for S2 plus. So just to make the S2 plus OP consistent, I will need a new field S3 plus in our theory. So the S2 plus answer is just written here. And similarly, from the S0 plus S3 plus OP, if we demand OP associativity, we can again show that this S3 plus phi OP must truncate at the quartic order in Z bar minus ZP bar. This relation. So again, so if you follow the same steps, you can see that for the S2 plus S3 plus OP to be consistent, you have to have a field S4 automatically existing in the theory that satisfies equation 50. So this, and of course the S4 phi OP has to truncate at fifth order. So by now I hope the recursive method is clear. So you see that for S2 plus Sk plus OP to be consistent, we need the automatic existence of a field Sk1 plus, where k is greater than equal to 2. So this is giving us the infinite tower of fields just from the demand that our S2 plus OP has to be consistent. Okay, so 51 is the generalization of what we have seen till now, and 52 is telling us that this Sk phi OP is truncating at the k plus 1th order. Okay, so again this truncation, this follows from this time constraint 53, and further I have decomposed this Sk plus object into anti-holomorphic mode expansion for now. So this is truncating at order k plus 1. So why the normalization is that? Because this will directly give us the precursor to the W1 plus infinity algebra. That's why this extravagant kind of coefficients. So importantly, all these semi-modes are holomorphic in the OP limit. Now, these SKE objects are not local Carrollian fields. So the Carrollian fields are really these quantities, SK plus, and they are just consisting of some new modes. Okay, and these SK plus fields has scaling dimension delta equal to 1 minus k and spin is 2. And so the holomorphic weight for SK plus as well as the semi mode is same, 3 minus k by 2. Now, if we iteratively use the procedure for deriving the S2S2OP or S2S3OP, we can get the S2SKOP directly as 55. And more interestingly, following a similar iterative argument, we can derive the most general SKSLOP to be this equation 56. And this is looking like okay. Now let us, so since we have seen that there is some time polynomial expansion for SK and SL, and the right hand side can also be expanded in time also. Now if we do expand them and compare this t to the power 0 t, p to the power 0 terms coefficient from both hand side, we recover equation 57. And when, so see there is still this weird quantity, this is still not z minus zp. Now if we explicitly impose t tends to minus infinity, this denominator becomes 1 by z minus zp for any t. So in the t tends to minus infinity limit, we have got the tree-level OP of the celestial conformally soft gravitons that was derived in this work. Okay, and this seems to be telling us that the 2D celestial conformal soft graviton primary, this, so this is a notation of this paper. So this is nothing but the object here, and this appears inside the S1 minus k Carrollian field. So remember, this is just an object, this is not a Carrollian conformal field. So this occurs inside a Carrollian conformal field. Okay, so just want to point out that this HKLOP, so as was done in the celestial CFT case, this was obtained from the general OP of two celestial conformal graviton primaries, but the derivation of the celestial conformal graviton primary OP was relying itself on some inputs from the explicit bulk theory. So at least they needed to fix the so they need to fix the pole structure that came from the collinear singularity limit, and that gave them the 1 by z1 minus z2 structure. So that's why I said that the derivation relied at least on some inputs from the explicit bulk theory, but we have no, we didn't need any hint from the bulk theory. We reached this semi-OP by an intrinsic 3D Carrollian CFT analysis, but under the two assumptions that I stated at the beginning of the section. So most important thing is the time. So the Carrollian time coordinate was the Carrollian time coordinate took the central role in the whole construction, because you see it's all related by time derivatives. Yeah. Time dependent. Okay, so yeah, so these are the assumptions. Okay, so no, I mean for you. And for you, Sabrina, they're just they're motivated from 2D CFT. Like, so as I said, in 2D CFT, you can do this kind of uh, symmetry analysis to get the TTOPs directly from symmetry principles. So you know the general form of T phi OPs, you make an unsuch, and then TTOP, and you use bosonic commutativity property, but you have to truncate the answer at some order. And there the truncation is done by assuming that mm, no field with h less than 0 exists. So if you don't use this assumption, then you cannot really fix this TTOP by symmetry only. So that was the unitarity assumption. So this is just motivated from that. So probably this has something to do with state operator correspondence. So I don't know. So I think only the time independent local fields in Carrollian CFT is like it's susceptible to state operator correspondence. And then if you assume this, then to uh, prevent the negative norm states from happening, you will impose this kind of, probably, I don't know, but it seems. And okay, so time, yes, there is no singularity in time direction as well as the anti-holomorphic direction. The singularities are only holomorphic. Okay, so uh, we will not need radial ordering here. So there was this temporal step function. So that will take care of the radial ordering. Like, no, so I have assumed the existence of this S2 plus operator, right? So this subleading. So this is not always the case, right? So yeah, yes. Yeah. And these are not really soft theorems in strict sense because, as I said, so to make the soft limit, you have to explicitly impose this t tends to minus infinity limit. So they have more to do with collinear limits. So I will come to that. Yeah. No, these are not universal. Yeah, probably. So I have assumed that no branch cut happens. So previously, when I was deriving the word identities, I have explicitly avoided the branch cuts. Probably they may play a role too. Uh, no, I mean, so I'm just referring to this reference by, okay, these two references, like this sub-leading sub-theorem is not universal even at tree levels. Yeah, so I mean, yeah, so the way, so this is the motivation, but the way I introduced like this relation, I don't think, I mean, there is any hint of sub leading here. I mean, that was just the motivation part, like why I am introducing the S2 plus. Yeah, if you have a field like this. So if you don't have this, they don't exist. Like S2 plus field. Like I'm trying to say that this S2 plus field will not always exist in the theory. Yeah. So, but when it exists, we have this infinite tower. Like when we consider examples of these two works, probably there it doesn't exist. No, I haven't thought about it from purely amplitude perspective. Or yeah, yeah. So ultimately, yeah, you can just make the collinear splitting function from all these considerations. Okay, so W1 plus infinity. Okay, so from there we can just compare the powers of anti-holomorphic coordinate and see that 50 it happens, and from a version of uh, OP commutation, from a Carrollian CFT version of the relation between OP and commutator map that was developed here, we can find that finally the mode algebra, modes are defined in 59, so finally the algebra of modes are given by 60. Okay, so and how to make it W1 plus infinity? Just use this releveling and you will find the W1 plus infinity. Okay, so there is a sub-algebra of this whole H algebra or W algebra, and those are uh, generated by the modes of the two universal fields S0 plus and S1 plus. So universal in the sense that since they are built from Carrollian Stress-tensor, they exist in all Carrollian CFT, so that's why they're universal. So from the modes of these two fields, we can have a sub-algebra of this W1 plus infinity, and that is the what? Okay, that is the semi-direct product of the SL2 or Catch-Moody algebra with the Abelian super translation. And okay, we also have some T fields. T fields, so that was capturing the equivalent information of the uh, celestial stress tensors. So finally, considering this T field also, the symmetry algebra is obtained to be the semi-direct product of Vir and the wedge algebra of the Catch-Moody algebra of the wedge algebra of W1 plus infinity. And now, how to relate them with soft theorems? Yeah, okay, so then let me quickly wrap up. So from these considerations, so like since this 55, equation 55 is valid for an infinite number of fields, so k is any integer, mostly negative in, sorry, no, mostly positive integers. So since 55 is valid for an infinite number of fields, I would postulate that there is one S2 phi OP like equation 61, where this phi1 field, phi1 dot is equal to phi exactly in the OP limit. So that means the generators that are contained in this field S2 plus is acting on the phi field by an inverse time derivative. Okay? So these transformations are non-local in time, but they are local in space because they are just space derivatives. Okay? And if we consider the S2 plus word identity, we can just demanding that this S2 plus X correlator is finite everywhere. I mean, when the points are non-incident, so they are uniquely fixed up to temporal contact terms by 62. And this is the Carrollian conformal version of the 2D celestial sub-subleading conformally subgraviton word identity. And of course, this S2E part in the explicit t tends to minus infinity limit when all the primary sub delta equal to 1 is equivalent to the sub-subleading energetically subgraviton. Now there are other fields Sk plus. So I can postulate this OP for Sk plus, and it is reassuring to note that there exist explicit examples for these kind of OPs, and they have recently appeared in this beautiful work. So I have some examples of these abstractly postulated OPs. Okay, so finally, I would like to say that the the word identity of the Sk plus fields, if you take the temporal Fourier transform and impose the explicit soft limit, you get an expansion like this. So this is looking like an shifted subgraviton expansion. The poles are mismatched. So F0 is Weinberg, F1 is subleading, F2 is sub-subleading. And so what to do? But there are also these omega to the power 0 terms that cannot be fixed from the knowledge of this SKOP alone, but they can be fixed from the knowledge of SK plus 1 OPs. So by recursion, we can see that for the SK word identity with k tends to infinity, and then if we multiply both sides of that word identity by omega to the power k, we recover the expression 66, and it is looking like the standard subgraviton expansion for the incomplete projected amplitudes. So this suggests that this S0 plus T field may be directly related to the 4D bulk AFS hard graviton, because we have to need explicit soft limit to find the soft graviton expansion. So that's all I wanted to say. So by further using the power of symmetry, I will say that you can find the collinear splitting function involving one graviton from these methods, and we plan to write about that on my ongoing work with Romain Ruggieri. So I just wanted to show how to holographically derive some aspects of the 4D AFS subgraviton physics directly from 3D Carrollian CFT.